Okay, I did some other videos on online with our media site, which is Tricey's video surface. They were just very blurry, so I'm going to try to do them again here. And for our Calc 3 class, and I'm just going to put these on YouTube. It's a little easier, and I can make longer videos. So there's that. Okay. So anyways, continuing on with Calc 3, now basically we're dealing with integration, and we want to integrate volumes instead of area. And the way we're going to do it is with repeated integrals, or the book calls them iterated integrals. And in this section, we're going to connect this to area. Okay, so first off, just integrating with a multivariable expression, and I title this dy versus dx. Okay. So it's kind of like partial differentiation. You're going to hold one variable as a constant and integrate with respect to the other variable, depending on whether you have dy or dx. If it's dy at the back of the integral, then you're going to integrate with respect to y. If it's dx, then you're going to integrate with respect to x. Okay, so let's look at the first problem in the old book, 0 to x, and we have x plus 2y dy. Okay, so in this case, the variable that we're integrating with respect to is just y. And so I'll go ahead and treat this guy as a constant. So if I integrate this, you could think of it as if it was a constant like 3. Okay, if you integrate 3, you get 3y with respect to y. So if you integrate x, you get xy. Okay, and then you integrate this one, business as usual, right? So 2y squared over 2. And we have to remind ourselves to evaluate. One of the weird things in this setting is now we have variables in the limits of the integral. Okay, so don't overthink it, just business as usual, right? So wherever I see a y, I'm plugging in an x. Okay. So you can literally think of this as going from y equals 0 to y equals x. Okay. Okay, so evaluating this guy, I have x times x, which is x squared. This simplifies, right? 2 over 2 is the same as 1 over 1, so I just have y squared there, and I'm plugging in an x wherever I see a y. So it would be plus x squared, and then subtract away, plug 0 in to both of these, and they're both just 0. And at the end of the day, we have 2x squares, right? Okay, so there's one. Let's look at another one, this time with respect to x. So I have the integral of y ln x all over x, and then dx. Y is presumed to be greater than 0, and we're integrating from e to the y to y. So you could literally think of this as x equals e to the y to x equals y. Right? And you're pretending the y is a constant. So really you could, if you wanted to, you could factor it out of the integral. I'm just going to leave it there though. In order to integrate this, I need to do a U-substitution. Right? So I'm going to let u equal the ln of x, and then du is 1 over x dx. Right? I'm going to multiply both sides by x, and I get x du equals dx. Or maybe I should have, yeah, no, that'll work. Okay, so I have then the integral of y times u all over x times what our dx is now, so it's x du. Okay. The x's will divide out, and you're left with the integral of y times u du. Okay, and you're just considering the y as a constant. You're integrating u, so it'll be y times u squared all over 2. And I need to evaluate that eventually, but I'm going to back sub first, right? So using this junk here, I'm going to get y times the ln of x squared all over 2. And I'm integrating from e to the y to y. Okay. Okay. So I'm plugging in for x, and so I'll get y times the ln of y squared all over 2, and then minus, well, y times the ln of e to the y squared all over 2, and then simplify as much as possible, right? That'll make your life easier. So here, I can't do much with the ln y squared part, so too bad. But I can, clean this guy up. So this will be minus ln of e to the y. Well, you're asking e to what power equals e to the y, and that's just y. So ln of e to the y, you can simplify into y, and you'll get minus y times y, which is y squared, and then it's squared itself. So y squared squared, it will be y to the 4th, and then that's all over 2. Okay? Assuming I didn't make any errors there. It just seems like I did. Did I lose something? Oh, I screwed this part up. Sorry. So this parentheses should be on the inside there. And then I'll have minus y times, this part is y squared. So, sorry, I'm smushing all this in. You have to make it really like this or the video isn't going to like it. It's going to be all screwed up. So, all right, so let me just rewrite that. Let me rewrite this part, right? So it's y ln y squared all over 2 minus y times the ln of e to the y squared all over 2. And what I'm saying again is that this part in here is just y. So the first part, there's not I could do about it, right? It's just y ln y squared all over 2. Okay, and then minus this part right here. So this will be y, so you'll have y squared, and then times another y, so that would be y cubed all over 2. Okay. Okay. So there's that business. Right. Now we want to actually look at some of these repeated integrals. And what you're going to see is one integral inside of another. And you're going to work inside out. Okay, so you do the integral first, and then work your way out. So 2. Now finally the iterated integral. And we're working inside out. So let's look at number 11. And we have the double integral of x plus y dy and then dx. The first integral is limit 0 to 2, and then the outer integral limit 0 to 1. Okay. Okay, so as promised, we have to do this portion first. Okay. Okay. So what does that equal then? It's the integral of this thing integrated with respect to y. So x is a constant, so that'll end up being xy, and then plus y squared over 2, right? Y squared over 2. And then I have to remind myself to evaluate from y equals 0 to y equals 2. Okay. And then I still have the dx part, so then I'll have to integrate the result with respect to x. Okay, so integral then of plugging 2 in for y. Okay, so I remind myself by looking over here, it's with respect to y. So plug 2 in for y. I'll have 2x plus 4 all over 2, which is just 2. And then minus plug 0 in for y, and you'll get y 0 plus 0, which is just 0. Okay, so I'll end up with this dx from 0 to 2. Okay, so then I'm going to evaluate this integral, and this is something we can do, right? This is the traditional Calc 1 integral. I could just rewrite that then 2x squared over 2, so that'll just be x squared plus 2x, right? And that'll be integrated from 0 to 2. Right? And then evaluate that, plug 2 in for x squared is 4. 2 into x there is 4. Minus 0 plus 0. And then that will just be 8. Okay? Unless I made some silly error, which seems, oh, it's 0 to 1. Sorry. Yeah. So the first limits were 0 to 2. This one is 0 to 1. So this will be 1 plus 2 minus 0 plus 0. Sorry about that. That's equal to 3. Okay. Let's try just 2 more of these characters, and hopefully you'll get some practice with them on your own. So number 17, we have kind of a trig version, 0 to the sine x, and then on the outer part, 0 to the pi, right? So here we go. We got 1 plus cosine x, and first we're going to go dy and then dx. This is kind of the classical ordering because you're going to end up with an integral in terms of x. Okay. Right. So first I have to integrate this thing with respect to y. Okay. So I'll have, and again, it's this integral first. Okay. Okay. So I'll have y plus y cosine x. And then I need to evaluate that from 0 to sine x. Okay, so if you wish, you can kind of put all that in parentheses and then dx. Okay. Then I need to evaluate this thing. And I would have the integral of y is y squared over 2. Sorry, we're inputting, right? So I'm putting sine x in here. So I get sine x. And then also in here. Times plus sine x times cosine x. And then you're plugging 0 into here and then 0 into here. And of course that will just be 0 plus 0, which is 0. So I don't have to worry about that part. Dx, and I'll have to integrate this from 0 to pi. You can use, there's trig identities for this. I'll probably just do a u sub. So let u equal sine x. I can integrate the first term, right? The integral of the sum is the sum of the integrals. So the first term, of course, is negative cosine x from 0 to pi. And then I'm doing a u sub on this guy. So du will just be cosine x dx, which is sitting right here. Okay? So I need not kind of worry about cancellations or anything. So this will be the integral from whatever to whatever of u du. Oops, sorry, lost off the screen. Okay. This part of it then, negative cosine of pi. So pi, cosine of pi is -1, negative 1 is 1, and then minus negative cosine of 0. Cosine of 0 is 1, so I have negative 1. And then plus this part, which will be u squared over 2. If I back substitute, I'll have sine squared x all over 2. And I need to evaluate that part from 0 to pi. Right? Okay, sine of x is 0 at 0 and pi, so this will just be 0 minus 0, which is 0. And that whole part will just be 0. And then this part would just be 1 plus 1, which is 2. And that would be your answer. Okay, something that comes up in probability, if you want to become an actuarial or something, you have to worry a lot about these probability functions. And you'll have improper integrals inside of improper integrals, and you'll have to kind of integrate those to figure out your probabilities. Okay? So you'll get items that look like this. If you're interested, you can, just Google actuarial. Become an actuarial, you have to take these tests, and the first test is a probability test, and you would see things like this. Okay? It's a hard test. I'm not going to lie to you. It's extremely hard. Okay? But it's an awesome job if you get it. You just work with numbers all day. You don't have to deal with people problems. Okay, so anyways, the deal with these, if you get an infinity anywhere, you can kind of just stop and say it's divergent, right? So when we dealt with improper integrals, they're either convergent or divergent. And we follow the same kind of rules here. So just focus in on this part of the integral, okay? And I'll convert that to a limit as b goes to infinity of the integral from 1 to b of 1 all over xy times dx, and then that's all inside of this outer integral with respect to y. So I need to integrate this character with respect to x, and that's just going to be the ln of the absolute value of x. So you can factor out the 1 over y, right? So it's going to be the integral of the limit as b goes to infinity of 1 over y times the ln of the absolute value of x, right? And then we are evaluating that from 1 to b, and then we need to integrate that thing with respect to y. Right? Okay, so here, then this limit will go to infinity as x goes to infinity, right? There's no way to get a y value that's 0 or something weird like that to cancel it out. You just kind of consider it as a constant. And so this part of the integral will be infinity. And as soon as you get some sort of infinity floating around, we're just going to say for us, you know, you're done. Okay, call it divergent, and that'll be the end of the story. Okay, so this right here will imply divergent and stop. Okay. Okay. Let's move on then to area now. So you may not have known it, but every time you figure out the area between two curves, you can rewrite that thing as an iterated integral. Okay, so section 3, the area of a plane region. Look, so recall your Calc 1 lessons and finding the area between two curves, or maybe that was Calc 2, right? So recall, let's say I need finding the area, and for example, we have y equals x squared and y equals x. So I want to find the area enclosed by these two curves. Okay, so these are simple curves. I can draw them pretty quickly. Y equals x squared is something like this. Y equals x, you know, it's going like this. And so I need to find this region here. Okay? Okay, so these integrals, when you're finding area, it's always going to be basically the top curve minus the bottom curve. And this is, this case right here, we're oriented with respect to x. So if you took Calc 2 with me, you'd remember me talking about the Riemann man running across in this orientation, picking up little rectangles, right? So you would be picking up rectangles where the bottom of the rectangle is given by this curve, the top is given by this curve. And so this particular rectangle here would be described, the area would be described if we consider this location x sub I, and then the width is change in x, and then we give the two curves names. So we'll give the y equals x, we'll call that one f of x, because it's the top curve, and the parabola g of x, because it's the bottom curve. Okay. The area of this particular rectangle would be, what is it? It's the top of the rectangle minus the bottom of the rectangle. So it's the top, it's this distance to here minus the distance to here, right? So it would be f of x sub I minus g of x sub I times change in x, right? And the Riemann man, what's he doing? Well, he has this bag on his back, and he's collecting all these little areas as he runs across from this intersection point to this intersection point. Okay, so his bag is basically a sum of areas, and what are the areas? Well, those are just these differences times this change in x. So it's just summing up these areas. And then if you smooth it out with the limit, then you get our integral, right? So the limit of this thing is the integral of f of x minus g of x dx from a to b. Okay, so that's that problem sort of revisited. But it is, it's the top curve minus the bottom curve in this orientation when he's running across this way. There's another orientation to worry about though, right? So in particular, if we had something like x equals y squared, and then again x equals y, and we're trying to find the region enclosed by those, it's not a perfect sort of reflection, right? To get these guys, it's a change in orientation, really. And you may think, oh, my running man is going from here to here, or maybe I don't know how it works. So the orientation for the running man now will be like this. Okay, and he'll be collecting again these areas and making a sum to approximate the area between the two curves, right? So the two curves this time in this orientation look like this, and you may, it's kind of hard to think about it, right? So you may think it goes like this because you think maybe this is a 90-degree rotation, but it's not. It's kind of a reflection and then a rotation or something like that, right? So the graph actually looks like this. The slope is going positive, it's going up, right, in this direction like this. So you just have to be aware. Let's put a little hat on them. And, in this orientation, the rectangles now, these a sub i's, let me go and draw the thing here. The top of the rectangle is given by this curve, so we could call this guy now f of y, and we'll say f of y sub I, so this would be some generic rectangle at location y sub I, and then it has a width change in y, right? So it'd be f of y sub I minus g of y sub I times change in y sub I, or just change in y if all the little sub-intervals are equal in length. And then what do? We have to go through and add them up. That's what the Riemann man is doing. He's collecting all these areas, and then we smooth it out with a limit, and that gives us our integral. And for us, maybe we're going from C to D now, of f of y minus g of y dy, right? Okay, so those are the two basic orientations. And what I'm saying now is you could convert these two into double integrals. Okay, so let's look at the conversion of this guy into a double integral. Okay, so I go back to now my example, y equals x squared, and then y equals x, right? So the picture is like this. Oops, I'm trying to find this region here. My orientation is like this. Okay. And my little rectangles are in here somewhere. So the top curve is this curve, the bottom curve is this curve. Okay. Okay. So for Calc 1, we would write, okay, top curve minus bottom curve, and then we integrate from intersection to intersection, right? So find the intersection points, just set the curves equal to each other. And of course, this would be x squared minus x is 0. And then we get x times x minus 1 is 0. And then we get x equals 1 or x equals 0. Okay. And I don't know, you can use those for your, okay, that's what I need. Okay, there it is. Right. Okay, so anyways, we need to then rewrite this as an iterated integral. Okay, so how do I do that? Well, if you think of this as going from point to point on the x-axis, we can kind of re-envision this as going from a curve to a curve. Okay, and everything in that case would be terms of y. So I'm going from the curve y equals x squared to the curve y equals x. And you put that into a double integral. Okay, so you're going from the curve y equals the bottom curve, which is x squared, to y equals x. And then in here, we'll just have a 1, and then we'll have dy and then dx. Right? Okay, and these turn out to be equivalent, right? Because if you turned around and then evaluated this curve, so if you turned around, whoops, and did that part of it, you would get back to where you started, right? So let's do that. Right? So 0 to 1. If you integrate this with respect to y, you'll just get y. And then I need to evaluate that from x squared to x dx, right? So evaluating this thing, first plug in x, and then plug in minus x squared. And sure enough, there it is. We could take this up even one more level and think about surface to surface, because this object here you could re-envision as a three-dimensional object with height 1, right? So the point is, if you have a cylinder with a height 1, okay, then the volume of that cylinder is actually equal to the area of its base. So you could take this up one more notch from this expression here and put it into a triple integral, which we'll do later. You'll have the integral from 0 to 1, the integral from x squared to x, of the integral from 0 to 1 of dz, dy, dx. If you don't believe me that works, just try on your own there to evaluate this thing right here. Right? You would get z, and then z from 0 to 1 would be 1 minus 0, which would put you back here. Okay? And what is this thing? Well, it's just saying basically that you're finding the volume of this kind of cylindrical thingamajig. Okay, so it would be this object here, but the height of it is just 1. Okay? So the volume here is equivalent to the area here. And that just goes back to this idea. The volume of a cylinder with height 1 is equal to the area of its base, right? Because volume is pi r squared h. And when r is equal to 1, the area will be pi r squared times 1. Okay? So it's some neat stuff. You can really get into it if you wish. Let's look at the other orientation, right? Because we'll be changing orientations in order to make some of the integrals easier. So let's try the same problem, except change the orientation. So I'll have the same problem, y equals x squared and y equals x. And I can draw it. Okay. But now I want to put my running man on the y-axis. Okay, like that. And here's my region that I'm trying to find the area of. I'm going to put these in terms of y. So the first guy, I'm going to take the square root on both sides. X is equal to the square root of y. And then on the other guy, I'm putting x equals y. Okay. And the square root of y is, part of this curve. It's just this part here. It's not the whole thing. Right? It's just the half. Put that in a different color. It's just this half. Right? It's not this half. Okay. So in this orientation, then, if I go to my double integral now, going curve to curve. You want to start with the bottom curve and then go to the top curve. So the bottom curve is x equals y, right? And this will be 1, we're looking dx now. So x equals y, and then you go up to x equals square root of y. Okay. Then the Riemann-man is running from point to point, intersect to intersect. So you can find the intersect by setting the equations equal to each other, and you'll just get with 1 again. Okay, so this will be from 0 to 1. Okay. And then if you integrate, you should get the same answer as what you got with the other integral. You went through and did the integration. So maybe we should do the integration. So let's take this guy here and extract them and actually integrate the thing. So I'd get x squared over 2 minus x cubed all over 3 from 0 to 1, which is 1/2 minus 1/3 minus 0 plus 0. And then this guy, I find common denominator, right? So this will be 3, this is 2. This will be 1/6. So we better get the same answer with the other integral. That's my point. So this guy here, the integral of, whoops, and this should be dy. So first integrate with respect to x, and I get x from y to square root y. And then I have dy. Okay. And then I'm going to plug in square root of y and y for x. So I get the integral of square root of y minus y dy. And then I'm going to integrate that stuff. So you get y to the 1/2 is now y to the 3/2 times 2/3. And then minus y squared over 2. And I'm evaluating from 0 to 1. Okay. So in that case, that being 2/3 times 1 to the 3/2 is 1, minus 1/2, okay, and then minus 0. Whoops, this is y squared over 2, so yeah, I'm good. Then I need a common denominator again. So I multiply top and bottom of this guy by 2. I get 4/6, this guy by 3. 3/6, and then out with 1/6, which is the same answer, right? All right, so awesome. Okay, sometimes one answer is much easier than the other. Let's start looking at more complicated problems. So find the area using the repeated integral. This is problem 35 from the book, and they give us an area of a rectangle, which we can just find geometrically, but we're going to use an iterated integral. Okay, so this point here is 8, 0, and then this point here is 0, 3. Okay, and the way I think of it is curve, it goes point to point and on the outside, and then curve the curve. So point to point, and the inside it's curve to curve. And you figure out kind of what the curves and what the points are dependent on what orientation you're in. So for example, if we do dx, or dy dx is usually the order we want to go in, because we'll end up in an integral with respect to x. So for this case, curve the curve, y equals what to y equals what. So y equals 0 is the x-axis to y equals 3. Okay, so I'm going from curve to curve, and my orientation when it's in this form will be like this. It'll be the traditional orientation, right? So curve the curve, in this case, is going y equals 0 to y equals 3. And then the running Riemann-man goes from point to point, getting the areas. Okay, so the Riemann-man is going from 0 to 8, and then we have 1 dy dx. Okay, so I integrate 1 with respect to y, and that'll just give me y from 0 to 3. And then I get y squared over 2. Okay, and if I plug in 3 there, it'll be 9 over 2, right? So let's just cut to the chase, 9/2, and then dx. Oh, sorry, y squared over 2. It's just, sorry, I integrated twice. Sorry, got carried away there. You're just plugging 3 in for y, and then minus 0, which will be 3. Sorry. Okay. And then I integrate that part, so that would be 3x evaluated from 0 to 8. and then plug in 8 for x, so I get 24 minus plugging in 0 for x, which is 0, and our answer is 24. Geometrically, you know it's base times height, right? So it's 8 times 3, which is 24, which is the answer we got. So it seems like it works. Okay, for the rest of the problems, we're going to be kind of given a region, and then we have to produce these integrals and switch the order, right? So this gives you a lot of good practice. So let's try 45. Sketch the region and then switch the order of the integral. So I have the integral from 0 to 4, and 0 to the y, f of x, y, dx, dy. Okay, so what's the deal here then? I need to sketch the region, and it's based off of these, the limits on these integrals. And I start with x and then go to y. When you start with x, you're sort of ending in the non-traditional orientation. So your Riemann man is going in this direction. Okay. Okay, so curve the curve, x equals, so you go with this for these, x equals 0, which is the y-axis, to x equals y, which is the diagonal through the origin. Okay, so I'm going from, let's see if I get some colors here, I'm going from x equals 0, which is this curve here, to x equals y, which is this curve here. Okay. And then the Riemann man is collecting areas based off of these regions from 0 to 4. Okay? So the Riemann man is going from y equals 0 to y equals 4. And that will enclose the region that we are worried about. Okay, so I need to now rewrite this in the other orientation. So where my Riemann man is now going in this direction. Okay. And for that to work, I'll go double integral f of x comma y dy dx. And you can imagine this as some surface hovering over top of this region here. Okay, so there's some surface in space, maybe over top of it. And eventually what you'll be doing is finding volume over top of this region, but underneath this surface here, given by f of x, y. Okay, so in the other orientation, I need to go from y now equals some curve to y equals some other curve. Okay, so in this orientation, I'm going from y equals x, this curve, to y equals 4, which is this curve. Okay. So y equals x to y equals 4. And then the Riemann man is going from 0 to whatever this point is. And I believe that's 4 as well. So 0 to 4. If you want to figure that out, you take, what is it, x equals y. So y, set it equal to 4, and it's obviously 4. Okay. So what is this point? It's 4, comma 4. Okay, so the Riemann man is going from 0 to 4. Okay, let's try another one. Okay. Okay, so we're going to have a lot of circles to deal with, and eventually that means we're going to have to worry about converting everything to polar coordinates. Okay. So this is 47, and I'm going from -2 to 2 in the inner integral 0 to square root of 4 minus x squared, and then I got f of x, y, dy, dx. Right, so the region this time I'm going y equals 0 to y equals this, and it's the non-traditional. It is the traditional orientation this time. Okay, so y equals the curve 0, which is just the x-axis. Okay, to y equals square root of 4 minus x squared, which is the upper hemisphere of a circle with radius 2. Okay. So it's that region. My running man is in the traditional orientation. Okay. So he's running then from x equals -2 to x equals +2 and collecting all of the areas between those two curves. Okay, I need to now switch it. And one thing I'm going to note is this y equals square root of 4 minus x squared, right? So if I got rid of the square root, I would get y squared equals 4 minus x squared, and then it's an equation of a circle, and there's always two hemispheres. There's a plus and minus, right? The minus y equals minus square root of 4 minus x squared is that curve right there. When I switch the orientation, I'm going to have to work with x equals the square root of 4 minus y squared, right? So if you were to solve this equation here for y, or for x rather, you would get this thing, right? So in my new integral, I have the orientation dx dy. The Riemann man is going now in this direction. I'm going to have to kind of extend this. He's running like this. Right? In this orientation, he's dealing with the curves x equals something to x equals something, right? So in order to pull that off, I need to have the thing in terms of x. And this equation is not the same as this equation here. This graph is not the same as this graph. Okay, so what graph am I really working with this time? That's this other hemisphere. That's the hemisphere that goes in this orientation like this. Okay. The negative square root 4 minus y squared would now be down here. Okay. So it's a little strange. The inner part of the integral is going from the curve y, or sorry, now it's the curve x equals something, right? So x equals, well, I can't use 0, right? Because I need this portion of the area. So I have to kind of use the other part, the x equals negative square root, right? So x equals negative square root of 4 minus y squared. I got to use that part of the curve as well. And where is that thing? That thing is the bottom. Okay, that's this guy here now. So when I go for x, it'll be the curve x. So the running man is collecting areas between, these two different curves here. He's collecting these rectangles, going from, well, I have to go from here to here now, and that will give me those rectangles. So the bottom curve in this orientation then is going to be the negative square root of 4 minus y squared, and then the top curve is going to be the positive square root of 4 minus y squared. And then the Riemann man is going from y equals 0 to y equals 1. Okay. So again, curve the curve, point the point in that orientation. And the other orientation, it was this curve to the hemisphere curve, and then from point to point. Okay, let's do another circle. We'll just do 2 more. Okay, so like number 55 then. They give you the integral from 0 to 1 of the integral from negative square root 1 minus y squared to positive square root 1 minus y squared. That's a circle with radius 1 we're dealing with. And then we have dx dy. Okay, so I want the region here. This thing here is, well, this thing is x equals negative square root 1 minus y squared. That's the lower hemisphere and the sideways orientation. Right, so the Riemann man You can think of him going in this orientation. Okay, the upper curve then, this is the bottom curve, then the top curve will be this other one. So I'll put it in a different color. Okay, it'll be this curve. So curve the curve and then point to point on the y-axis. X equals negative 1 minus y squared to x equals, negative square root 1 minus y squared to x equals positive square root of 1 minus y squared. And then the Riemann man is running from y equals 0 to y equals 1. So that's going from 0 to 1, okay? And that'll be this region right here, the same region as what we were dealing with before. So I need to change the orientation back to kind of our usual orientation, which is like this. And you think of it as curve the curve and point the point. And you want to do it in a way such that you get this area. So if you try to put like negative square root 1 minus y squared, you're going to have this curve, and then their top is square root 1 minus x squared. You'll get this curve. You don't want to do that because you'll have too much area, right? You need to make sure you go from x, or rather in this case, y equals 0 to y equals square root 1 minus x squared. So our new integral then, we have dy dx. Butchered that. I'm going from now y equals 0 to y equals the square root of 1 minus x squared. And then the running man is going from negative 1 to 1. Okay? And why is it 1? It's because this thing kind of gives you x equals 1 minus y squared. And then if you, I square both sides, I get x squared is 1 minus y squared. And that object there, x squared plus y squared equals 1, is a circle with radius 1 centered at the origin. Okay? One more. So 57, go integrate from 0 to x and 0 to 2. We have dy dx, and then plus the integral from 2 to the 4, and then 0 to 4 minus x dy dx. Okay, so this integral in this orientation is kind of bad. You don't want to have to do two integrals if you can just pull off one integral. Let's look at what this region really is, right? So the Riemann man going from y equals to y equals, curve the curve on the inside is going to be this orientation here. Okay, so curve y equals 0, which is the x-axis, to y equals x is this curve. And then I'm Riemann running from 0 to 2. Okay, so that'll be this region here. Okay, and then this integral is telling me I'm Riemann running from 2 to the 4 here, where the bottom curve again is the x-axis, and the top curve now is 4 minus x. Okay. You'd probably have to experiment a little bit to figure out where that is, but I've already done the problem enough. I know that the curve is just going like that. And we end up with these two regions. Okay. So the deal is with this integral is the top curve and the bottom curve, well, the bottom curve is the same in both regions, but the top curve changes. So you have to change your integral to represent that. Note, if you go in the other orientation, though, you don't have to worry about that issue. The top curve is always the top curve as you go from 0 to 2. Right? It's always this curve. The bottom curve is always the same bottom curve as you go from 0 to 2. So it simplifies your integral. I just need to solve this thing for the other variables. So originally y equals 4 minus x, and our new orientation will be x equals 4 minus y. Right? And so the bottom curve is originally y equals x, now x equals y. So I'm going dx dy. So x equals y to x equals 4 minus y. So x equals y to x equals 4 minus y. And then the Riemann-Man is going from 0 to 2. Okay, so get a lot of practice doing that. Get a lot of practice doing the integrals. I've done billions of integrals, so I'm not going to do a whole bunch more unless you ask me to. And then, yeah, I'll do a bunch of integrals for you. But I'm tired of doing integrals, so unless you say, hey, Mr. Stroop, put some videos up where you do some integrals, I mean, I'll do that. But unless you say so, I'm probably not going to do it. So we'll leave it there, and we'll pick up with worrying about volume next time. So this is still like Calc 1 stuff. It's like kind of like, oh yeah, so what? We'll take it up a notch next time. Okay, thanks for watching.